Professor Hartman here again. So what I'm going to do now is go ahead and work through some of the problems in Chapter 6. This deals with the concept of momentum. Momentum, right, which is basically just equal to mv, is what, on some level, what people thought force was before Newton. Well, it's not what the force is, but it is still an incredibly useful quantity. Like energy, momentum is one of these things that is sometimes conserved. And when it is conserved, you can use, well, conservation principle to solve problems. So let's go ahead and jump right into these here. All right, so this is out of chapter 6, number 3, out of the book. So you're told that a 7,150 kilogram railroad car is traveling alone on a level frictionless track with a constant speed of this. A load is initially at rest, is dropped into the car. They want to know what's the car's new speed going to be. So the really important point to point out here is that momentum, right? So momentum is given by the letter P, and P is conserved, right? So you want to know, when is momentum conserved? It's conserved when the net external force on a system is equal to 0. That's the only condition under which momentum can be conserved. So in this case, right, we have the railroad car. I'll sort of just like think of it like this. This is the railroad car. I'll call that mass m. And this is moving with some initial speed v initial, right? And we know what that is. That would be 15 meters per second. And there's another smaller mass, let's call this mass, little m, right? That's sort of dropped into this thing. Now, momentum is conserved in the x direction because there's no friction. So what I would do here is I would say, look, momentum in the momentum is a vector, so we have to look at x and y. So px is conserved, right? The x momentum is conserved because there is no horizontal force. There is no x force, right? There is a force acting in the y direction, right? So the momentum in the y direction is not conserved. Because gravity acts on little m. Right? Gravity acts on little m. So you can have momentum conservation in one direction, in this case the x direction, but not have momentum conservation in the y direction. So we're going to look at the x direction here, right? So what I'll do is I'll say p initial, right, in the x direction is equal to p final in the x direction. Now, in the initial state, the load, right, little m, has no x velocity. So all the momentum in the x direction is exclusively due to the train. So that's going to be mv initial. In the final case, right, this thing is now in there, right? So the masses are combined. That's little m little m plus big M times v final. Right, this is the initial momentum, this is the final momentum, and we're looking for v final, so we can divide both sides by the sum of the masses. In that case, right, we get that v final is big M v initial over the sum of those masses, big M plus little m. And we'll go ahead and plug in what we got, right? So big M is 7150 and little m is 3350. So we'll say, okay, this is 7150, right, kilograms, times 15 meters per second. And then down here we have the sum of those two, right? 7150 plus 3350. They're both kilograms, like that. And we'll go ahead and we're just going to plug in numbers, see what we get. So I'm going to do that here on my calculator. So 7150 times 15 divided by the sum of those masses. So let me just, 7150 plus 3350. And we get a smaller velocity, obviously, about 10.2 meters per second. So that would be the velocity there. Okay. That's the answer to that one. So very simple momentum conservation. This is also an inelastic collision, right? So this thing is sticking to that. So energy is not conserved here. It's important to point out, right? Momentum can be conserved, but energy is not conserved. So if you were to calculate the initial kinetic energy of this system, and then the final kinetic energy of the system, you'd find that it would have lost kinetic energy. Now, where did that energy go? Well, it basically is lost to friction and, to heat and sound and that kind of thing. Okay, so number 8. An atomic nucleus at rest decays radioactively into an alpha particle and some other nucleus, right? So, I don't know, let's say that we start out with X, right? This is nucleus X. We don't know what the element is. And they want to know what will be the speed of the recoiling nucleus if the speed of the alpha particle is that. And they're going in the opposite directions, right? That's sort of the assumption here, I think. So this is element X, and it's going to radioactively decay, and it's going to split into 2 particles. One of them is going to be an alpha particle, right? I'll do that with the Greek letter alpha. And another one, well, I don't know, we'll call this nucleus Y, right? And so this is the deal. So this one, we'll call this the velocity due to alpha, and we'll say this is the velocity due to Y. And this is, the sort of thing that happens in particle physics and nuclear physics all the time. You get these radioactive decay events. An alpha particle is just a helium nucleus, just in case you were wondering or forgot or had seen it before, maybe in chemistry or physics at some earlier point in your life. Okay, so momentum is conserved here, right, in the x direction, because there's no external force acting on the system. And the initial momentum is 0, right? I mean, that's sort of an important point here. So we have an initial momentum of 0, and the final momentum, well, it's split into 2 pieces, but these 2 pieces had better sum to 0. So what we're going to do here is we're going to say, okay, P initial equals P final, like that. And then we're going to say, well, P initial is 0, right? And P final is going to be the mass of Y times the velocity of Y, right, plus the mass of the alpha particle times the velocity of the alpha particle. And what we're looking for here is we're looking for the velocity of Y, because we're given the velocity of the alpha particle. So let's solve for the velocity of Y, right? So the velocity of Y here, if I do the algebra, what I will get is this. It's minus m alpha v alpha over my. Okay. Now, we have a number for the velocity of the alpha particle. We don't have numbers for these masses, but we have a relationship between them, right? We're specifically told that the mass of nucleus Y, I think it's bigger, right? It's 57 times the mass of the alpha particle. So we can plug that in there, right? So what we're going to get is that this is negative the mass of the alpha particle times the velocity of the alpha particle divided by 57 mass of the alpha particle, and the alpha particle mass will go away, and what we know what v alpha is, it's 2.8 times 10 to the 5, so put that back in there, 2.8 times 10 to the 5, so we'll get that the velocity in the y direction, right, is minus 2.8 times 10 to the 5 meters per second divided by 57, so let's see what we get here. So 2.8 times 10 to the 5 divided by 57, and we get a grand total here of about 4912, let's say approximately 4,912 meters per second. Okay, so that's how you would do that one. Let's move on to number 30 rather. Okay, so here you're told that you make an elastic head-on collision with a second ball at rest, and it is going to rebound with a speed equal to this of its original speed. And they want to know what's the mass of the second ball. Okay, so let's do it this way. Let's call the mass of the second ball big M. We'll call the mass of the first ball little m, right? So this is little m. Let's say it's moving at V initial there, like that, okay? And this is going to be big M, and its velocity is 0. So its initial velocity is 0, right? It's not moving, 0 meters per second. And it's elastic, so they don't stick together. This is the initial state, right? The final state is that it's going to be moving in the opposite direction, right? So here, what we're going to do is we're going to have little m is moving like this. Let's call that V final 1. And then we have big M, right, that's moving like this. And we don't know what that is, right? We're going to call that V final 2. We don't know what either of these are. However, we are told, okay, so we'll just leave it at that. So now, because momentum is conserved here, but so is energy, because an elastic collision, a perfectly elastic collision, does conserve energy. So first we'll do momentum is conserved. So P initial equals P final, like that, right? And so what we're going to get here is that the initial momentum, well, that's just this piece, because this piece has no initial momentum. So that's going to be mv initial. And the final momentum is going to be the sum of these momenta here. And what we could do, and I think this might be, is since these momenta are vectors, is basically call anything to the right positive, anything to the left negative. And so here we can say, okay, this is going to be mv final 2 minus little mv final 1. And then we can make life a little easier by saying, well, look, v final 1, right, they're told that this is 0.45 of the initial velocity. So I can sort of replace that in there. So I'm going to go ahead and sort of plug that in there. And so we'll get that mv initial is equal to this thing here minus little m 0.45 the initial. And so I could simplify this, I guess, a little bit more by saying it like this. So this is m like this. I'll put the coefficient out front. That's just kind of standard operating procedure. Okay. Now I can gather this thing on this side, right? So I can basically add this piece to that side. So it's going to be 1.45 mv initial equals mv final. Okay, now we don't know anything else, right? Yeah, that's all we know for the moment. Okay, and we're looking for, the idea is we're looking for v initial, right? That's I think what they want. What was the, sorry, we're looking for big M, sorry. That's what we're looking for. Let's see here, we got to the speed. Okay, cool. All right, so now we got to do, this is equation 1. Now let's go move on to energy conservation, right? So also, because this is elastic, the initial kinetic energy equals the final kinetic energy. For the initial kinetic energy, it's just a little ball, right? Because the big one is stationary. So this is going to be 1/2 m v initial squared. And then the final kinetic energy is the sum. This is a scalar, so we don't have to worry about direction. We just make them both positive. This is 1/2 m, 1/2 little m v1 final squared equal plus 1/2 big M v final 2 squared, or v, yeah, okay. So I guess I'm putting the 1 here. The halves will cancel out. There's a half everywhere. And then again, I'm going to use this substitution right here, and I'm going to basically go ahead and plug that in there. So there's a bit of algebra. There's a lot of algebra here, more algebra than physics ultimately, which is what a lot of these problems end up being, unfortunately. It's just the way it goes. So this is going to be 0.45 the initial squared plus m, like that. Okay. So now I'm gonna square the 0.45 basically. I want a number for that. That's going to help me out. So 0.45 squared in my calculator, I'm going to do that. That is 0.2025. We'll just call it 0.20. Well, I guess let me see. So this is going to be let's just say 20 m, like that. And now again, I'm going to bring this piece over here. I'm going to subtract it. So this is like a coefficient of 1 there, so it's going to be 1 minus 0.2, which will be 0.8. So I'll have 0.8 mv initial squared equals big M v final 2 squared. And, okay, so now I can solve for v final 2, right? So if I go ahead and do that, right, so v final 2, right, that's going to be v initial times the square root of 0.8, and then it's going to be the ratio if you kind of do this algebra out. You get something like that. Now I could make this even a little easier, because the square root of 0.8, not easier, but a little neater, I guess you could say. The square root of 0.8, that's going to be say about 0.89. So I could rewrite this the following way, that v final 2 is 0.89 v initial times the ratio of these masses, right? M over big M. Do we know any of these masses? Let's see. I don't know if we do. No, we don't. Make it as hard as it could possibly be. Okay, so I'm going to take this thing, right, this expression here, and I'm going to go ahead and plug it into there. And presumably the masses will all cancel out. They better, because otherwise we're in trouble. But I think they will. Okay, so that's the left-hand side. The right-hand side is this V final, which is this mess, right? So it's going to be 0.89 V initial. Well, not all the masses, but a lot of the masses will cancel. It's looking pretty good. Okay. All right, so this is what we got. So the VI's cancel, because there's one on each side. So that's good news. And now, what I'm seeing here is that I have a problem, which is I don't know if I'm going to be able to eliminate all my masses the way I'd hoped. So let me see if I made an error somewhere. I don't see that I did. Little m over big M. Got to this point, so you get to see me do this in real time. I know it's very exciting to see this, because the way I'm looking at it now is, no, is that right? Looks like I'm going to have an extra little m floating around. You don't give us that, right? Where's the mass of the second ball? Where did I mess up? So let's see. Bear with me for a second. Final. I don't see where I screwed up. Well, let's proceed and see if maybe I'm not as bad as I think it is here. Because we're looking for big M. Maybe we can only get it as a fraction of little m. That's sort of what I'm thinking. That's where I'm going to go with this. I'm going to go ahead and assume that I didn't make a mistake, because I don't think I did, and just pick up here. So 1.45 little m, that's going to equal, okay, 0.89 big M times this stuff here. So I'm going to square both sides, because I want to get rid of this square root. So if I square both sides, I'm going to do this again, right? So 1.45 squared. That ends up being 2.1. So this is going to be 2.1 m. And if I square this side, I get this 0.89 squared, right? That's going to be, well, I already, about 0.8, right? So that's 0.8 m squared. And what that does is it gets rid of that square root. Sorry, there's a square there as well. And so some stuff will cancel, right? So basically this will cancel out one of those powers, and this will cancel out one of those powers. And so what we end up with is this, that 2.1 little m equals 0.8 big M, and then you could divide both sides by 0.8. So this is going to be 2.1 over 0.8 times little m, right? So let's see what that is. So 2.1 divided by 0.8. That gives us 2.625, and so big M is 2.625 of little m, right? So it's a little more than 2.5 times the small mass. I think this is the only way to do it, because I think we're missing. You can only get one in terms of the other, I believe. Yeah, that makes sense to me, because I don't think I made a mistake here. I think it's pretty good. Okay. So, well, actually, I'll do this one later. So I think that's a long enough, video for the moment, I guess. All right, so I hope you found it useful, and keep the eye out for some more coming up.